so far, but also kind of present some ongoing work and some things that are very much in progress. So just also before we start, if you do like to have me as a video on, if you put it down in that bottom right hand corner in that white square, I shouldn't overlap with anything important on the slide. So feel free to do that, but also feel free to turn off the video. So today I'm talking about large prehistoric tephra deposits, and I'm mostly going to be talking about what I've been doing in terms of the Mazama eruption. So that's from Crater Lake, which explains the photo in the background. So the next 30 to 40 minutes, I'll be talking about the following topics. So I'll start by kind of introducing why I think it's important to do this research, so the kind of motivation. I'll then give a bit of background about the Mazama eruption itself, and then I'll talk about the kind of main part of the thesis so far, which has been integrating distal and also proximal tephra deposits, and with a kind of focus on some of the sources of uncertainty and some lessons learned. And then the final kind of two parts of my talk are very much work in progress, which will hopefully spark some discussion, but those will kind of cover how I've been using ash dispersion models, but also hoping to improve how I've been using them. And then finally, a kind of perspective on the hazards and especially the long-term impacts of eruptions of this scale. So as I said, I think it's nice to think about why we actually do the research that we do. So a bit of motivation, in other words. So whilst we're much more likely to experience small eruptions more frequently, I think it's still really important to study larger events, as obviously they can happen and they will happen. So it's important to not just focus on things that we're perhaps more familiar with. And perhaps in a time like coronavirus, it's even more evident that we do need to study kind of black swan and less likely events in terms of us being prepared for when they do happen. So on this slide, I've just highlighted this paper here by Chris Newall and others, where they talk about the impacts of VEI7 eruptions, which is the kind of scale we're talking about today. And then I just like to include this infographic because I find it quite helpful for getting my mind around the kind of scale over which eruption magnitude spans. So for example, today, we're not talking the kind of very upper end of the scale, something like Toba, the kind of super eruption. As you'll see, Mount Mazama is a relatively smaller blob, but we are kind of scaling up from things that we're perhaps more familiar with on the right-hand side of that infographic. So again, just to kind of put things into context, I'll talk through a bit of some eruptions we're perhaps more familiar with. So Mount St. Helens, 1980, everyone will have heard of. And again, it's on this right-hand side of the infographic, so it comes under kind of VEI5, magnitude 4, so on. And this was a great opportunity to kind of demonstrate the utility and usefulness of going out in the field and collecting data, which was done, obviously, after the eruption. And this data became very useful and was, helpful for using in empirical models. So I've just shown one example here, where David Pyle calculated the volume from thickness data, for example. And going back to my project, what I'm interested in is how these methods and these approaches will still be useful, but perhaps need some kind of extra thoughts or some other way of dealing with data when scaling up to yet VEI7, so 2 orders of magnitude larger. Another eruption that everyone will be very familiar with, and you'll see is kind of on the lower end of this infographic, is Eyjafjallajökull, which was an eruption in 2010, which I'm sure everyone remembers. And the kind of research side of this was a great opportunity to look at some of the improvements that we'd been kind of working on in terms of ash dispersion models. And it was an opportunity to kind of calibrate them and test them in terms of, we had great satellite observations and retrievals, in addition to kind of ground-based sampling. And it was found that, yeah, these models are becoming increasingly sophisticated, but a lot of them, do remain operational, useful for volcanic ash advisory centers and so on. So again, going back to my project, what I'm interested in is how these existing models will deal with much bigger eruptions, much bigger inputs, and thinking over larger scales. So just now, finally, to get us thinking in this big eruption kind of zone, I've included these kind of 2 images here. So this is a photograph taken looking out over the crater lake, and it's just kind of an imagining of what the pre-eruption topography would have looked like. So I always find it a little bit challenging to get my head around the fact that there was an edifice there, for example, before the eruption. Perhaps another fun way to think about the proximal scale is to use the outline of the caldera lake and the crater in perhaps an area I'm more familiar with. So whilst I have been to Crater Lake, I spend most of my time here in the UK in Bristol. And as you can see, overlaying that Crater Lake, you kind of swallow up the center of the city. So this just helps me thinking of how big this eruption was. And whilst these are kind of proximal perspectives, we can, use that knowledge to think how long distance the impacts would have been. So that kind of leads me on to now introduce the eruption itself. So Mount Mazama, that pre-eruption volcano, it was located on the western edge of North America. And then 7,700 years ago, we had this caldera forming eruption, and that's what's left behind the beautiful Crater Lake you'll have seen in the images prior. And what's quite useful from my perspective was that the position of Mount Mazama and then the predominant wind directions actually led to a lot of the tephra being deposited on land over a really large area. So that's quite useful in terms of this is the data we have to work from, and it's handy to be able to go into the field and access it easily as opposed to needing offshore drilling and so on and so forth. So that's what's shown in this plot here. The kind of visible extent of tephra, so where you can go and actually see it in the field. But I've also included these 3 sites, which are cryptotephra sites. So this is tephra that's not necessarily visible to the naked eye. You might have to dissolve it out of your ice core, for example, or use some kind of extraction methods on your peat bog samples. But again, this is just driving home that message of how far reaching these impacts would have been following this eruption. I also just want to take a moment to kind of acknowledge that this was an eruption that was observed, and people obviously have lived in North America for much longer than this time period, so prior to 7,000 years. And this is actually evident in the kind of observations that have been passed down of this eruption. So this is just an example of an oral legend, but we can clearly see that there are observations of seismicity and of tephra fallout, for example. So I think it's really important to keep this in mind when studying eruptions of this scale, in particular when discussing things like hazards and impacts as we move forward. So I'm now just going to talk a little bit about the kind of start of my thesis, and this is also kind of accumulated in a paper, that's come out of my PhD. So I won't go into every single detail, just in terms of not boring everyone in their daily talk slots, but there is an accompanying paper. So if you want more detail into exactly how I've done things, please feel free to see that. So lots of our kind of early understanding of this big climatic eruption was based on some actually really early work that was done by Howell Williams, and I'm sure a lot of other kind of field assistants and so on, actually back in like the 1940s. So what I'm showing here is the isopack map. So isopacks are contours of deposit thickness that was created at the time. This was kind of since revisited by Simon Young, who was a PhD student here in the UK, and whilst he did it slightly differently in that he split the fallout deposit into 2 units, you can see that the kind of broad depositional pattern is towards the north and towards the east. And just to kind of show a site that, for example, I've since revisited, shown by this blue star, this is kind of what you see when you're in the field. So this is, again, the kind of fallout deposit, so really nice, well-sorted pumice. And just for the sense of scale, this is, over 3 meters at this distance. So a really substantial deposit. So this kind of tephra work, in addition to, I guess, more traditional geological mapping by Charlie Bacon and many others, has led to our understanding of the eruption itself. And I guess you could think of it as a kind of textbook caldera collapse. So we started the eruption with our kind of Plinian phase, which, as I said, Simon Young's picked out two different units within that. But then we also had a column collapse at some phase, and that produced the wineglass welded tuff, if people are familiar. And then towards the end of the eruption, obviously we had the onset of caldera collapse, and this is sometimes referred to as the ring vent phase, and would have been characterized by very large pyroclastic density currents, and likely a corresponding co-PDC plume. So what my project's been actually looking to do is to integrate this really excellent record at the, I guess you would call it the proximal scale, with the really extensive distal record. And why that's important, well, for big eruptions such as this, actually a really significant proportion of the tephra and our kind of knowledge, our data, is in this distal region. So, you know, areas beyond 100 kilometers. And it's really worth thinking about integrating the two. So obviously I'm not the first person to do this. So what I'm just showing here is a compilation of previous efforts. Again, I'm showing this in the format of isopac maps. So this is again, thickness of the deposit. But hopefully what you can see here is there's kind of been a range in how people have interpreted this deposit. And often what you do end up with are these kind of minimal extent maps, which is kind of what I showed earlier. So what I was hoping to do was to kind of revisit this problem and perhaps take some new approaches. So the way in which I did that, the first thing was to kind of start to compile a database of where tephra has actually been recorded, Mazama tephra obviously. So that's what's shown here in this animation on the left-hand side of your screen. And I've just shown it in terms of when these records were kind of made available. So these range from publications to scientific reports, as well as PhD theses, master's theses, and so on. And the reason for it being so widely reported and extensively studied is that it's not only of interest to us as kind of volcanology, geological-minded people. So as I've just included a few examples here from this database, but it's used just to simply date a sedimentary sequence. A kind of fun area that is used is archaeology. So this is a really cool example, I think from Fort Rock Cave in Oregon, of some sandals which were found below the tephra layer, for example. So we know that they're older. And other disciplines that use it might be paleoecology, paleo-environmental reconstructions, and so on. So whilst that's really excellent in terms of, it means we have over 150 sites in which Mazama tephra has been reported, it does mean that not everyone has recorded and observed the tephra in exactly the same way. So as geologists and volcanologists, something that's kind of second nature to us is to record the thickness of the deposit that we're observing, but that's not really of interest if you just need to know that the tephra layer is there and something above it or below it is younger or older. So that's that same database that I showed earlier, but this time it's populated with where thickness has actually been measured, and that's shown by the color, the actual thickness. But hopefully what you can see, and you would agree with, is that there's quite a bit of complexity in terms of where we're getting very thick and very thin tephra. Overall, as we'd expect, as we reach more distal regions, we are getting thinner tephra, but you can see there's quite a bit of variability, for example, up in this area. And that's probably our main explanation for these different isopacs that have been drawn that are just kind of cycling through here. So I wanted to figure out why that is and why that might be. And that required some field work. So obviously I'm not able to visit every site that's in this database, and that would have been most of my PhD in a car. But I did do some kind of targeted field work. So in particular, as I pointed out, this region has a lot of variability. So that's where I did one of my kind of field visits. So we're now up in northeastern Oregon, southeastern Washington, I always get that wrong. And here are some of the kind of things that we encountered. So as you can see, the Mazama tephra stands out quite nicely in the landscape. It's this really white material. But what we found quite interesting was a lot of these sites aren't actually recording the primary fallout. So as you can see here, we've got about over a meter of tephra. Here we've got over 3 meters. And here is just a pit of tephra that's been excavated by a badger. But what was quite interesting and I think quite informative for me was, whilst from an outcrop scale, so kind of the scale you can see it in these photographs, you can quite clearly see that this isn't a primary deposit. It's associated with alluvial deposits, for example. We can see that it's likely come from upslope or upstream. When you look at the tephra kind of at a more hand specimen scale and then furthermore on the SEM, there's actually very little evidence that it's been remobilized or moved from its initial position. So for example, there's no contamination by background sediments, and there's no real evidence of sedimentary structures being developed. So whilst, as I said, from an outcrop scale, we can quite confidently say exclude these thicknesses. If you were to just encounter this tephra in an isolated sample, or perhaps in a lake setting, it might be more challenging to confidently say whether it was primary or secondary. And I think that's what's led to the inclusion of some of these thicknesses in our construction and interpretation of the thickness. So with this kind of field knowledge in mind, I kind of went back to the database and went through the localities and classified whether it was likely that they recorded a primary fallout or if they'd likely undergone some secondary process. And that's again what's shown here. And the symbol corresponds to these classifications. As you'll see, in some sites, there is kind of the combination of two by these mixed deposits, but also there are a lot that are still unknown. So I guess this is kind of something that's constantly a work in progress and can be expanded on and worked on further. What I then did with this data and the kind of classifications I gave it was to use it to construct isopachs, so that similar way of interpreting deposits, of contouring the thickness. And the way in which I did this was just using the kind of fitting of a spline surface. So that's just one way in which we can slightly minimize the user bias of hand drawing them. But in the kind of main goal of this was just to show how sensitive any method of isopach construction is to the actual data that you start with. So here is that spline fitting isopach method only using the primary thicknesses. And here I've just repeated that same process, but using all of the thickness available. So now you can start to see how subjective and kind of sensitive these methods can be to our actual starting data. And then from isopachs, typically what happens is that people then calculate erupted volume. Again, there's a range of methods that you can choose from to do that. I've just shown one example here, which is the pile approach, which I showed earlier, of fitting like 2-segment exponential decays to the area enclosed by these isopachs. And again, as I said, irregardless of the method you choose, it's quite clear that it's actually the starting data that will influence the final result. So whilst these plots look quite similar, if you integrate under them to get the total erupted volume, you get 150 approximately if you just use primary data, and then an additional 24 cubic kilometers if you used all the data available. And yeah, that's quite a significant volume, just bearing in mind that something like Mount St. Helens, the total erupted volume is just over a cubic kilometer. So we're talking quite large margins of error and uncertainty. So that might sound a little bit overwhelming, and that there's so much to be kind of cautious about when dealing with these deposits, but hopefully what I kind of have shown and given a taste of today is that there are ways to deal with this. So as long as we're quite careful with our sources of uncertainty at different points, we still need to use this really valuable field data. So as I said, for me, I think it's really important to remember the first source of uncertainty is that data that we're using. So we need to think about how likely it is that we're recording our primary thicknesses. The next stage and the next time that we're introducing some new subjectivity, uncertainty, is when we're fitting and drawing isopachs. And then, as I said, there's this next step, which is the method in which you then go on to calculate things like erupted volume. But as I said, it's very important that we still do this process, as our field data is still our actual, best thing to work from. We don't have satellites or anything like that, so we have to use the field data, but just cautiously. So I'm now going to talk a little bit about some other things we can actually gain from either going in the field or using other people's field data. So this is that same database, now populated with where grain size has been recorded. And why would we be interested in grain size? Well, it can actually tell us quite a lot. It can tell us perhaps about the fragmentation mechanisms that have formed the material. And something that I'm really interested in, and perhaps we'll focus on for this talk, is that it tells you a lot about how the tephra and the material has been transported, but also how it's actually been deposited, how it's ended up on the ground. So what do we actually expect to see with our grain size? So Typically, we would expect that the further you get from your volcano, the finer grained your material becomes. And you can think of that as relating to the kind of terminal velocity and the support of your clasts in your plume. And this is something that has been observed in deposits. So this is an example from Fogo, so in the Azores, and some work by Steve Sparks and others. And as you can see here, getting further away from the volcano, we do get finer grain sizes. And just a reminder here that on the phi scale, large numbers are small grain sizes. This is also observed in other deposits. So this is an example of a Hecla layer, so an Icelandic tephra. And again, you can see that the median grain size is reducing as we get further from source. But interestingly, you do start to see that the rate of change of grain size is not constant. And especially when we're getting out to the kind of distal reaches of these eruptions, of these deposits, our trend is quite different to what we're seeing close to source. So if we now think about this in the context of the Mazama tephra, I'm now only highlighting these sites where I've actually measured the grain size distribution. And the reason for that is just that I'm quite confident in the data quality, but also I have access to the full grain size distribution, which isn't always published, especially in the multidisciplinary nature of the sources. And we can also add in some data that was collected by Simon Young during his PhD. As I said, he was mostly working on that more proximal record. But as you can see, we're starting to build up this plot here again of median grain size and distance, where we're seeing a nice reduction as we get further from source. But then there seems to be quite a dramatic change to when we're in the more distal reaches of a very constant grain size. So there's something interesting there. You also will have spotted there are some gaps in this plot and in general in this database. Unfortunately, this kind of key area where we're obviously having a transition in our grain size trend, I don't have any records as of yet. So if anyone does know of any sites there, that would be great to know. But overall, we can kind of get the main trend, which is in the distal portion of this tephra, we're having a very stable grain size distribution. And one way that we might start to think about that is that our very fine material is no longer settling as individual particles. So the kind of Stokes settling and terminal velocity reliance is no longer our kind of key bit of information here. And why do we then end up actually getting any tephra on the ground? So it's, the argument is that the settling velocities of these individual particles can't overcome the turbulence of the atmosphere, but it's still settling out. And that can be explained by a range of processes. Perhaps people will be most familiar with aggregation. So it's a really interesting observation, this kind of distal tephra grain size. And it's also something that's not unique to the Mazama tephra by any means. So for example, it's also something that we observe in perhaps a deposit everyone's a bit more familiar with, so the Mount St. Helens 1980. And again, everyone will remember that this is a complex deposit. We have bimodal deposits, we have secondary thickening, but still beyond a certain distance, the kind of distal ash is kind of this very constant grain size. And this is quite an important observation and also might be quite useful because if we're thinking about ash dispersion models, which is what I'm going to be talking about next, particle size is a really important input parameter. So if we're interested in distal ash, which is my main focus, it might be quite nice to know that our parameter isn't changing too much as we get further from source. So as I said, that kind of leads me on to this kind of final part of my talk, these two sections which are very much a work in progress, so hopefully will spark some discussion. But the first of which is how I'm actually hoping to use ash dispersion models. And why I'm interested and why I want to use them is perhaps for two main reasons. So you can run an ash dispersion model for your eruption of choice and then predict where we would have our tephra fallout. And perhaps that would be useful to compare against the field data I've compiled, and it might give us some more insight into where we have thickened deposits, remobilized deposits, and so on. But it's also quite important to start to explore and develop these models for dealing with big eruptions. As I said, they're now really quite well trained and calibrated against things like Eyjafjallajökull. But what would we be doing if we had a bigger eruption? How would our models be behaving? And presenting their results. And why might it be that it's more challenging to use these models for big eruptions? Well, I'd say that there are kind of three main points that I need to introduce. So the first of which being any model requires input parameters, and for the case of ash dispersion models, those typically are called eruption source parameters. And these are already actually quite difficult to constrain, especially with quantitative uncertainties for modern observed eruptions, and that's kind of for a variety of reasons. But those kind of challenges are amplified when dealing with big prehistoric eruptions. And perhaps most importantly, when thinking of big eruptions, simply using an advection diffusion model, which is what a lot of ash dispersion models are, we're missing out a really complex plume behavior, especially in the more proximal record. But for the case of big eruptions, proximal can actually extend for long distances. And finally, a way to kind of overcome some of these challenges is to often run your models in kind of reverse mode. So work backwards from your field data to get estimates, for example, of your eruption source parameters. But as I've said in this talk, our field data is actually quite uncertain in and of itself. So you can see there's a bit of an issue with that approach, but it is still quite valuable. So the thing that I've been kind of doing so far has been this first challenge, tackling this first aspect. So how do we constrain eruption source parameters for big eruptions in the past? So here are some kind of 4 very important ones. Obviously, exact eruption source parameters will be somewhat model dependent, but I'm pretty confident that these are 4 ones that will be required for most ash dispersion models that you try. So I'm just going to kind of talk through my thought processes and my progress so far, but also kind of point out some kind of questions that are cropping up as I go through this exercise. So constraining the erupted volume or the erupted mass, as I said, that kind of links back to what I've been doing already, which is improving, hopefully, estimates of erupted volume. But there's still a few things that we need to think about. So I introduced at the start that this eruption had multiple phases. So ideally for a modeling approach, we would want to treat those somewhat separately. But it's unclear, especially in the distal record, the exact proportion of which belongs to each, belongs to each phase. So that's something I'm currently working on. We also need to think a bit about time constraints, because typically these models require eruption rates. So yeah, there's a time component, which as of yet is a bit, which will always be somewhat poorly constrained. So now moving on to particle size distribution, I've shown how I've started to compile various data sources. And then typically what people would do and what people would want would be a particle size distribution to input into your model. And one of the ways that we could do that would be to generate a total grain size distribution. Again, there are multiple ways to do this. I'm just showing one here, which is the Voronoi method. But there lies a bit of a question there of what we actually want. So if we took all the data available and produced a total grain size distribution, obviously we end up with quite a coarse grain size distribution because that proximal data is extremely coarse. But that might not be what we need. We might be more interested in, as I said, this kind of distal ash distribution. But where does our distal begin? That's kind of a bit of a sliding scale. So that's our important question to ask ourselves when constraining particle size distribution. There are also considerations about what the maximum grain size will actually be modeled by the model that you choose. And if anyone tuned into Jen Saxby's talk earlier in the seminar series, we also might need to consider things like particle shape, which will obviously significantly affect how particles sediment. And this next eruption parameter, the plume height, is perhaps the one that opens up the most questions in terms of this kind of links into that problem that we have of advection diffusion models not always incorporating the spreading of plumes. So if we were thinking of a smaller eruption and we had our field data and that was all we had available, we might use some kind of empirical models to estimate plume height. Perhaps the earliest of which was the Carey-Sparks model of 1986, but this really wasn't designed with eruptions of this scale in mind. And just to kind of demonstrate that point, I'm using some of the data collected by Simon Young here and showing how this model really does break down when you have very big clasts and very big eruptions moving really large distances. So we need to use other approaches. There obviously have been big improvements to these empirical models, as well as new approaches using field data, which I hope to kind of look into going forward. There are also a few other questions we need to ask ourselves. So what actually is the maximum height of a volcanic plume? In terms of when we reach really high levels in the atmosphere, what are the interactions between the kind of temperature inversions and so on? We also need to think about where our mass is actually spreading. And importantly, as I said, our model choice and the absence of plume spreading will be the kind of big factor in how key this input parameter is. And finally, most ash dispersion models require metadata, so weather data, which obviously we don't have for the time, so we quite heavily rely on reanalysis data. And this is just a way that I've compiled some data so far. So these are weather profiles at Crater Lake, again, modern reanalysis data. So you could arguably cycle through multiple wind profiles and find one that kind of works. But in general, the best knowledge we have of the wind is where the deposit actually went. So in general, we should actually be looking for things that can explain why our deposit is, for example, mostly to the north and to the east. So again, that's something I'm kind of in the middle of doing. And again, there's still some questions that remain. How likely is it that this weather is representative of the time period? And perhaps a kind of abstract question is, what would the orographic effects of this big pre-collapse edifice have been? And would there have been a lot of kind of local turbulence having a strong effect? So as I said, this is a very much work in progress, and hopefully we'll get some discussion at the end. But there are a few things I've been trying so far. And I think, as I said, it's just a kind of case of working through these stages and kind of constraining as best we can the eruption source parameters. So I'm now just going to close up the talk with a bit of a perspective on some hazards, with an emphasis on the kind of longevity of these following a big eruption. So as I've said, most of my talk has been about tephra, so obviously I'm interested in tephra hazards. And here I'm just showing the table of terminology and the kind of key impacts associated with tephra fallout as a hazard. And this is sourced from the Volcanic Ashfall Impacts Working Group, which I believe is a kind of IAVC, USGS, and other partners put together. And what I think is a little bit alarming, and as I said, maybe it's a catchphrase hard to get my head around, is that even over 2.5 centimeters, sorry, we're into this heavy classification of impact. And when thinking of that in the scale of the Mazama fallout, you can see that we're getting heavy to very heavy and into severe impacts over such a large scale. So Oregon, Washington, and Idaho, for example, are all encompassed in these isopachs. And now just taking a look at some kind of key localities that kind of drive home this message is even 100 kilometers from source, we're still getting 64 centimeters of primary fallout. So this is a tephra pit that I dug just near Mount Bachelor. And so it's quite obvious that even 100 kilometers, which in the grand scheme of things is still a significant distance, was undergoing these severe impacts. If we look a bit further afield, so now we're up to 500 kilometers, still directly along the dispersion axis, of course, we're still getting up to 20 centimeters of primary fallout. And that's again in this kind of heavy, very heavy classification. So roof collapse risk and the environment, sorry, would be essentially unworkable. Perhaps impressively, for this scale of eruption, we still get moderate impacts really far from source. So I think this is a site up in Banff National Park. Unfortunately, I've not visited, but is nicely documented. Here we have over a centimeter of primary fallout. So again, in these moderate classification of impacts. And just to kind of give a taste of what that would have looked like, this is what 2 centimeters of fallout looked like following Mount St. Helens. So again, pretty dramatic if you're experiencing this 1,000 kilometers away. And perhaps unique to this scale of eruption is the very, very distal impacts and the area over which we're going to be experiencing trace or dusting amounts of tephra. Again, following the Mount St. Helens eruption, areas that kind of were classified based on the thickness are places such as Billings in Montana, so a significant distance away. There was 3 millimeters of ash, and people were, reporting irritation, and it even closed some schools. So whilst I think it's quite clear that these initial and quite near instantaneous impacts would have been really catastrophic and substantial. I'm also interested in the more long-lived hazards that would have persisted over longer timescales. And my interest for this was kind of sparked by that early fieldwork that I did, trying to imagine how these deposits actually came about. So this is a nice compilation over thinking about the kind of drainage effects and drainage reorganization that would follow a big eruption such as Mazama, put together by Pearson and Major. And it's likely that these two deposits, which are, as I said, quite massive, no obvious sedimentary structures or things like that, likely happened into this process of the kind of hill slope reorganization. But as you can see, the kind of processes that were moving this tephra around can persist for over decades, over hundreds of years. So it's likely that this was an uninhabitable or at least very unpleasant environment for quite a long time following the initial deposition. And another secondary and perhaps long-lived hazard we need to think about is ash resuspension. So whilst we don't necessarily have kind of eyewitness accounts of this happening, I would argue that it's probably quite likely that it did following the Mazama deposition. And the reasons for that are that the kind of environments that we see modern day resuspension, so quite dry areas, would have been the kind of environment that the Mazama tephra was deposited in. So as you can see, the vegetation is in a kind of deserty and tundra-like environment, which is kind of perfect for remobilizing that tephra by surface winds. So the ash resuspension, in addition to this reorganization of your drainage network, even at very distal regions would have been lasting, the effects would have lasted for centuries. And there is some evidence of this. So areas up in the Great Plains, which is, I believe, up near the border with Canada, there were sites that were abandoned immediately after the eruption, and no one really returned there permanently for over 500 years. So it was clear that this was a very unpleasant place to call home. So hopefully I've kind of given you a taste of what my PhD entails, and I've covered a few things that I've thankfully got published so far, but still some things that are very much a work in progress. So I guess my closing remarks would be that whilst field data is messy, especially when dealing with these big, large, old deposits, it is an essential kind of exercise to go through. And as long as you're quite considerate of your uncertainty and where you're making certain choices, it can, still lead to quite valuable interpretations. Hopefully I've showed that it's possible to start challenging this, to start trying to tackle this challenge of getting eruption source parameters, and that will hopefully lead towards a somewhat guided way of using ash dispersion models for this eruption. And finally, I've kind of given a bit of a taste of some of the work I'm doing with tephra hazards, which will hopefully be expanded on at Cities on Volcanoes. But the main take-home message there is that these hazards were obviously catastrophic, but also we need to think about them in terms of spatial and temporal scales, and that's perhaps unique to big eruptions. So I've just left my email up there, but hopefully we can also have some discussion now or in the Slack channel.
Thank you so much, Hannah. That was really great. The questions are now open, and while people gather their thoughts on that, I posted the Slack channel that Hannah mentioned this in the chat channel. So if you want to link that, it's also at the end of most of the emails that you get. All right, looks like we have a question from Marissa. She asks, why aren't there sedimentary structures or secondary alteration in the reworked material? This is a question in the chat too. And in the absence of those, how did you conclude they were reworked?
Yeah, I think that's a really good question. I was quite surprised that there wasn't much contamination in terms of when I mounted up the samples and looked at them on the SEM and so on. So to me, that would suggest that it was something that happened quite quickly, but also I guess that the grain size distribution of those deposits is quite narrowly unimodal, so that perhaps isn't conducive to developing many sedimentary structures. So yeah, I guess my summary answer would be, I think it happened quite quickly, so there wasn't really time for the development of those structures, perhaps like slumping, quite rapid gravity downslope movement. And then also, yeah, this grain size distribution wasn't really the thing that was going to pick out any structures that did develop. So yeah, I was surprised also that there wasn't much more evidence for that, but I think there may be some ways to explain it.
Thank you. The next question, we'll go back to the chat, Shalharitz, and he asks, you presented volume calculations using David Pyle's method. Did you try and compare calculated volumes using other methods? For example, Nathanson 2017. Are there differences between the different methods significant? And how do you account for erosion in outcrops where you measure tephra thicknesses? So a few questions there.
Yeah, so the first part of that question, which was, did I try other methods? So I didn't by any means do all of them, but yeah, I tried different. So the Ash Calc package has lots of different functions that you can fit to IcePack data. So I tried some of those. I also tried essentially just using the spline surface and calculating the volume under that, as opposed to the kind of two-step method, which requires you to draw ice packs and then use that data. And there is actually quite a big variability, especially when comparing that spline method, which is likely because the proximal, which is probably very thick, is underrepresented using that approach. I think still the biggest source of uncertainty and range that I found was changing the data that I actually started with, but still, yeah, your choice of method does lead to some difference in your calculations. And the other part of the question, which was how do you account for eroded deposits? Again, it's a good question. I guess in the approach that I've taken, I'm assuming that they're all minimum and that we're probably missing some volume overall, but I think that's probably true of a lot of work on past eruptions, because a lot of these thicknesses as well will have been compacted to different degrees. So I don't know if that's a very satisfactory answer, but I haven't necessarily accounted for it consciously, but I've assumed that I'm probably missing some material somewhere from erodibility.
Thank you. Other questions? Please feel free to use the raise a hand function if you want to ask something too. I'll ask a question as well. I was really intrigued by the finds as you go further from the volcano and the implications for aggregation. And I was wondering if you could comment on, I know the median kind of leveled off, but are there any other subtle effects? Did you notice componentry changing? Did you notice maybe skewness in the distribution or anything like that?
Yeah, that's a really good point, and it's actually a kind of drawback of those plots, because yeah, the median can mask a lot. But overall, those distal deposits are pretty unimodal, so that's why I didn't go into that in too much detail. But in terms of, yeah, the skewness and the proportion of kind of ultrafines, I haven't necessarily seen anything, any trends as such. It seems to just be a very constant grain size. But that's definitely something to look at. In terms of the componentry, less so where I have the leveling off of the grain size distribution, but those few samples that I had slightly closer to source, I do see quite a concentration in the crystals. So there's definitely some kind of essentially dumping of crystals at a distance, which I now can't remember the exact distance, but yeah, there are definitely changes in componentry.
Thanks. All right, any last questions or thoughts? Well, please, let's thank Hannah again. This was a great talk, and we're looking forward to hearing more about the dispersion stuff as it comes out. Yeah. And also further discussion can be handled in the Slack channel, and the invitation's there. It's also the end of most of the emails. And so what I'll do is I'll just close it now, and but if some folks want to stick around, Hannah, usually like one or two people have questions that they wait to the very end. So if you want to hold on for 1 second here, we'll just do that. But everybody else, please take care, and we'll see you next week for Yoshi's talk. Thanks. Thanks for a great talk. That was fantastic.
No problem. It's a very strange experience talking to yourself.
I taught this last term, and it was very strange. Yeah.
Great presentation, Hannah.
Oh, thanks, Sam. Hi.
Good to see you.
Yeah, nice to see you.
Hey, Hannah, nice talk. I was just wondering when you're looking at the distal data and you mentioned aggregation. So aggregation certainly can happen, but do you need it to be happening, or are we just seeing more of essentially like diffusion out of the bottom of the plume?
Yeah, no, that's a really good point. I guess I just put aggregation there as one way to explain how it does get down. But yeah, as you say, there's that kind of ongoing diffusion from the bottom of the plume. There also could be other ways of enhancing that sedimentation.
Mm-hmm.